In rocket science, it's not always about bigger and more complex. Sometimes the simplest solution is the most genius one. Today, we're diving into something called monopropellants. It's basically a single liquid that packs all the punch you need to get around in some of the wildest environments you can think of. So the big question is, how on earth can just one liquid do the job of two?
Okay, picture this. You're floating in space right next to a satellite, and you've got to make this super tiny adjustment, like just a little nudge, to make sure its antenna is pointing back at us on Earth. So how do you do it? There's nothing out there. No air, no ground, absolutely nothing to push against. It's one of the biggest puzzles in space travel, for sure.
Well, the answer is this really elegant, simple idea, a monopropellant. Think of it like this. It's a single chemical that has all the energy it needs already locked up inside its own bonds. You don't have to mix anything. It's a complete, self-contained little power pack, just waiting to go off when you need it. So how exactly does one liquid pull all this off? It kind of seems like magic, right? But of course, it's not magic. It's chemistry. Let's pop the hood and take a look at the secret sauce that makes this whole thing tick.
Now, the first thing to get straight is that this stuff isn't burning in the way we usually think of it, with fire and oxygen. Nope. This is a process called exothermic decomposition. Basically, the liquid is, it's chemically unstable. It's just waiting for a reason to fall apart. And with a little nudge, its chemical bonds just snap. They break apart super fast, releasing a ton of energy as a jet of hot gas. And that gas, that's your push, that's your thrust.
And this slide just lays it out perfectly. Over on the left, you've got bipropellants. This is probably what you picture for those huge rocket launches, right? You need two separate things, a fuel and an oxidizer, and they have to be mixed just right to get that big boom. It's kind of like a car engine. But then, on the right, you have our hero, the monopropellant. It's just so much simpler and usually more reliable. It's just that one liquid and, a lot of the time, a little something called a catalyst to kick off the reaction and get the party started.
Okay, so for a really long time, this whole field was basically dominated by two big players. You can think of them as the old-school veterans of the monopropellant world. They are incredibly good at what they do, but man, each one comes with some pretty serious baggage.
First up, we've got hydrazine. Seriously, if there was a monopropellant Hall of Fame, hydrazine would be the star quarterback, no question. For decades, it has been the go-to choice for all those little thrusters that steer our spacecraft.
So why is hydrazine so popular? Simple. It's powerful. It gives you a massive amount of push for its weight, what engineers call a high specific impulse. But, and this is a huge but, all that power comes at a steep price. This stuff is extremely toxic and really expensive to handle safely. It's a major, major risk for the ground crews and not great for the environment either. All right, let's talk about the other old-timer on the block, hydrogen peroxide. Now, just to be clear, this is not the stuff you find in the brown bottle in your bathroom cabinet. Oh no, we are talking about a super concentrated, high-test version. And it has an amazing history. It was a huge deal back in the early days of rocketry. So fun fact, hydrogen peroxide actually powered the turbopumps on the German V-2 rocket during World War II. When it decomposes, it just breaks down into hot steam and oxygen, which is, pretty clean all things considered. Now, it doesn't give you quite as much bang for your buck per pound as hydrazine does, but it packs a serious punch in a really small space. Engineers call that a high-density impulse, and it makes it awesome for when you need to build something compact.
Okay, so that's the chemistry lesson out of the way. Now for the fun part. Where do we actually use this stuff? You might be surprised. The applications are way more varied than you'd think, taking us from the total vacuum of space all the way down to the crushing depths of the ocean.
This is really where monopropellants shine. They are perfect for when you need to make these tiny, super precise adjustments in places where there's no oxygen. I love this analogy. Think of them as the scalpels of the propulsion world, definitely not the sledgehammers. And in space, this is their bread and butter. Every single time a satellite needs to pivot to talk to us on the ground or swerve to dodge some space junk, or just, hold its position perfectly in orbit, that's called station keeping, by the way, it's firing these tiny little thrusters, almost always using a monopropellant like hydrazine. It's happening right now, all the time, thousands of miles above our heads.
But check this out. Here's one you probably didn't see coming. Submarines. Yeah, submarines. So, for a non-nuclear sub to stay underwater for a long time, it needs power that doesn't need air. And guess what works perfectly? Monopropellants. They use stuff like autofuel in what are called air-independent propulsion systems.
It lets them run their engines and stay hidden down in the deep for weeks on end. Pretty cool, huh? So as awesome and powerful as those classic fuels are, the sheer toxicity and danger of something like hydrazine has really pushed scientists to find a better way. I mean, it had to happen. And this has kicked off a whole new quest, a search for the next generation of cleaner, safer, so-called green propellants. You know, the funny thing is, the challenge they're facing today was actually defined way back in the 1960s. Back then, pretty much everyone agreed that there was a hard limit. The thinking was, if you want more power, you need a chemical that's so unstable it would be an absolute nightmare to handle. And for a long, long time, that idea just stopped people from even trying.
But now, with all our new materials and brand new catalysts, engineers are starting to tear that old assumption apart. And a super promising rookie has just stepped onto the field. Nitrous oxide, and yes, I mean the exact same stuff they use to boost race cars and, well, the same stuff you might get at the dentist's office.
And the reasons to be excited about nitrous oxide are pretty compelling. First off, it's way, way safer to handle than hydrazine. Its performance lands in this perfect sweet spot right between our two old-school veterans. And what's even better, when you mix it with the right fuels and use these new catalysts, it can actually start to compete with the performance of much more complex systems, all while being a whole lot greener. At the end of the day, picking the right monopropellant is all about trade-offs. It's a big balancing act, and you can see it laid out right here. You want the most power possible? Hydrazine is your go-to, but you're dealing with high toxicity. Need a lot of punch in a small package? Hydrogen peroxide is great for that. And then there's nitrous oxide, which really looks like the future. A much safer, cleaner option with just massive potential. It's totally changing the game for engineers. And all of this brings us to one final and I think really important question. As we start seriously planning missions to the Moon, to Mars, and even further out, figuring out fuel is going to be a huge deal. So could these newer, cleaner, safer monopropellants be the actual key to making spaceflight not just more powerful, but more sustainable for everyone? I'm talking about the people here on Earth and the astronauts out there. The future of how we explore space could very well depend on the answer.